Nuclear pulse propulsion. Let's start with one of the wildest, most explosive ideas for interstellar travel: nuclear pulse propulsion. Yes, you heard that right, nukes. But instead of leveling cities, they're being repurposed to send us to the stars. The idea of using nuclear pulse propulsion for interstellar travel is pretty simple. Take a spaceship, drop a nuclear bomb behind it, detonate the bomb, and use the explosion to push the spacecraft several light years into space. Sounds reckless, right? Well, it isn't as wild as it sounds. The concept was first proposed by General Atomics in the 1950s under a project called Orion. In case you are wondering, Orion wasn't like one of those sleek NASA spaceships you see in movies. It was a literal flying tank designed to ride the shockwaves of nuclear explosions. Crazy? Maybe. Genius? Definitely. So how does it work? The magic lies in Newton's third law. For every action, there's an equal and opposite reaction. When a nuclear bomb explodes, it releases an enormous amount of energy. If you direct that energy toward a giant sturdy plate at the back of your spacecraft, called a pusher plate, it would create a massive push and propel the spaceship forward. Now, you might be thinking, wouldn't that destroy the spacecraft? Good question, but that's exactly where the pusher plate comes in. It's made of super durable materials and has shock absorbers to dampen the effect of the nuclear explosion. But why go nuclear when we already have fuel to power our rockets? Well, getting to other stars is not as simple as getting to the International Space Station. Rockets powered by hydrogen fuel, like the ones we use to launch satellites or astronauts, just don't have the juice to make it. While they are great for getting off Earth, liquid hydrogen cannot propel rockets for interstellar travel. Nuclear pulse propulsion has an insane amount of specific impulse, a fancy term used for fuel efficiency in space travel. If everything goes well, it could propel a spacecraft up to 10% of the speed of light. In case you're wondering how fast that is, it's 20,000 times faster than a commercial jet. And if we ever achieve this kind of speed, we could reach the nearest star system, Alpha Centauri, in about 44 years instead of tens of thousands. Coming back to Project Orion, it wasn't just an idea, but rather a real program run by some of the brightest minds of the mid-20th century. And even the British-American theoretical physicist Freeman Dyson even discussed it in 1968 in a paper titled Interstellar Transport. The plan was simple: build a spacecraft powered by hundreds, even thousands, of nuclear bombs. Orion could carry massive payloads, making it perfect for long-term missions or even colonizing other planets. In fact, at one point, there was talk of using Orion to send humans to Saturn's moons by the 1970s. You heard it right. If it had worked, we might have been sipping lattes on Titan. So why didn't Project Orion happen? First, there was the small matter of detonating nuclear bombs in Earth's atmosphere. Not exactly great for the environment, or international relations for that matter. The Partial Test Ban Treaty of 1963 effectively grounded Orion by banning nuclear explosions in space. Secondly, there was the engineering problem. While the concept is solid on paper, building a spacecraft that can survive repeated nuclear detonations without turning into a fireball is, let's say, complicated. And let's not forget the public perception problem. Selling the idea of blasting nukes into space to your average taxpayer is a tough pitch. But suppose none of that problem existed. Could it work? The answer to that question is absolutely yes. The physics behind nuclear pulse propulsion is correct, and the idea remains one of the most practical methods for interstellar travel. But it's not a zero-risk plan. There's the potential for catastrophic failure, not to mention the diplomatic nightmare of launching nuclear bombs into space. But the rewards are pretty big too. I mean, we are talking about the ability to send massive spacecraft to other planets, moons, or even other star systems. Nuclear pulse propulsion could be the key to making humanity a multi-planetary, or even interstellar, species. Imagine a future where we're not just exploring the cosmos, but settling it. Building cities on Mars, mining asteroids, or even sending probes to distant exoplanets. Nuclear pulse propulsion is like that one friend with crazy ideas that might actually work. Sure, it's risky, sure, it's unconventional, but it's also one of the most promising ways to go beyond our solar system. So, the next time you look up at the stars, remember, the journey to reach them might just begin with a bang. A nuclear one, though. Warp drive. Let's now talk about something that sounds like it was taken straight from the script of a sci-fi blockbuster. The warp drive. So, what is a warp drive? How could it work? And why aren't we already cruising through Alpha Centauri? A warp drive is a hypothetical propulsion system that allows a spacecraft to travel faster than light by warping space-time itself. But isn't faster than light travel impossible? Well, yes and no. According to Einstein's theory of relativity, nothing can travel faster than light through space. But a warp drive doesn't move a ship through space. It moves the space around the ship. Imagine space as a giant rubber sheet. A warp drive would stretch the sheet behind the ship and compress it in front, effectively creating a bubble of distorted space-time. Inside this bubble, the ship stays still while the universe does all the moving. The general concept of warp drive came from John W. Campbell in 1957 when he wrote the novel Islands of Space. But it was the physicist Miguel Alcubierre who first proposed the idea in 1994 in the science journal Classical and Quantum Gravity. He called it Alcubierre Drive. The idea involved creating a warp bubble around a spacecraft. Here's how it works. The space behind the bubble expands, the space in front contracts, and everything inside the bubble is carried along like a cosmic surfboard riding a wave. But things are not as simple as they sound. The Alcubierre drive requires something called negative energy or exotic matter to warp space-time, and the negative energy isn't something you can just pick up at your local hardware store. It's a hypothetical form of matter with properties that seem to defy the laws of physics, like having a negative mass. Oh, and you'd need a lot of it. Early calculations suggested you'd need more energy than exists in the entire observable universe. Not exactly practical, right? But don't lose hope. Recent revisions to the theory have brought those energy requirements down to something slightly less absurd. Instead of needing a universe's worth of energy, you might only need as much energy as in a star. Quite some progress, right? And even if we somehow manage to gather the energy, there is a high chance that creating a warp bubble could destabilize the surrounding space-time. And by destabilize, I mean potentially ripping the universe apart. So, are we anywhere close to building a warp drive for interstellar travel? Not yet. However, researchers are exploring ways to make warp drive theories more feasible. For example, some scientists are investigating whether tiny warp bubbles could be created in the lab using advanced quantum field theories. Although warp drives exist only in theoretical physics currently, and we might get to see them even in this century, the fact that we're thinking about the idea, studying it, and trying to make it a reality means humanity is well on course to the stars. Asteroid hopping. Asteroid hopping is not the latest extreme sport, though it does sound pretty cool. This is a real concept for interstellar travel, and it might just be one of the most practical ways to explore the cosmos without needing a warp drive or some sci-fi magic. So, what exactly is asteroid hopping? At its core, asteroid hopping is exactly what it sounds like. Using asteroids as stepping stones to travel across vast distances in space. Instead of building one giant spaceship that needs to carry all the fuel, supplies, and resources for an entire interstellar journey, you'd hop from one asteroid to another, resupplying and refueling along the way. Think of it like a cosmic road trip. Instead of packing everything you'll ever need for the journey, you stop at intergalactic gas stations. Except these gas stations are icy rocks racing through space. Like the previous two interstellar travel ideas we have discussed so far, the idea behind asteroid hopping is quite simple too. In the first step, you need to find the right asteroids to serve as gas stations for your interstellar travel. Finding the right asteroids means a chain of small celestial bodies that have the resources you will need during our journey, like water ice for fuel, metals for repair, and rocky caves for shelter. Once you reach an asteroid, you'll start mining for resources. Water ice, for example, can be split into hydrogen and oxygen to create rocket fuel. This means your spacecraft wouldn't have to carry a lifetime supply of fuel and could be refilled at each stop. Or, should I say, asteroid. After refueling and resupplying, you'd launch off the asteroid head to the next one in the chain, and eventually make your way across the solar system, and even beyond. Asteroid hopping is a big deal because it solves some of the biggest problems of space travel. For example, one of the main reasons interstellar travel is so difficult is how much fuel it requires. Carrying enough fuel to reach another star system would make spacecraft ridiculously massive and inefficient. But if you can refuel along the way, problem solved. Another big plus about this method is that it's sustainable. Asteroids are just floating rocks. They are filled with resources. By mining them, astronauts could build and repair spacecraft, generate water and oxygen, and even produce food in hydroponic systems. Another big problem in this kind of travel is radiation. Space is full of deadly radiation, but some asteroids could provide natural protection, acting as cosmic bunkers. So, if there are so many benefits, then why haven't we heard of an asteroid hopping mission by NASA yet? For starters, asteroids aren't exactly lined up in neat rows, waiting for us to hop from one to the next, and coming up with a viable route with accessible asteroids requires advanced navigation technology. Secondly, extracting resources from asteroids isn't as simple as it may sound, and you would need special equipment to mine and process materials in microgravity. And the last major issue with this idea is the time. Asteroid hopping is not a quick solution. The distances we are talking about in this case are huge, And even with the perfect chain of asteroids, the journey would take several years or even decades. While we may not yet be fully ready to use this method of interstellar travel, NASA's OSIRIS-REx mission and Japan's Hayabusa 2 have shown that it can become a possibility in the near future. Asteroid hopping might not be as flashy as a warp drive or as dramatic as a nuclear explosion propelling your spacecraft, but it's practical, achievable, and a stepping stone, both literally and figuratively, to humanity's future in space. So, the next time you look at the sky, remember that the tiny specks of light might one day be our pit stops on the way to the stars. Bussard Ramjet. Imagine a spaceship that fuels itself as it goes, like an interstellar road trip where every highway is lined with infinite gas stations. The Bussard Ramjet is a theoretical engine that could propel a spacecraft to near-light speeds using nothing but the raw materials already floating in space. The idea was first proposed by physicist Robert W. Bussard in 1960, who said that the spacecraft would have a gigantic scoop, a funnel that stretches out for kilometers, possibly even hundreds of kilometers. The scoop used in this case wouldn't be any scoop, but rather a magnetic one to use the magnetic field to collect free-floating hydrogen. Think of it as a huge vacuum cleaner that would suck up the hydrogen particles as it moves through space. Bussard proposed that the collected hydrogen would be compressed and sent into a fusion reactor. That's where the magic happens. The fusion reactor would initiate a nuclear fusion reaction by combining hydrogen nuclei to form helium. It's the same process that powers stars, including the sun. As a result, a tremendous amount of energy would be released that would be used to propel the spacecraft forward at unimaginable speeds. In theory, the Bussard Ramjet could continue its journey indefinitely, as long as there's enough hydrogen in space to scoop up. The Bussard Ramjet is an exciting idea because it means the spacecraft would not need to carry any fuel, as it will be capable of generating its own fuel along the way. And since it'll be nuclear fusion powering the spacecraft, the Bussard Ramjet could potentially reach speeds up to 20% the speed of light, making trips to nearby stars possible within a human lifetime. So, what's stopping us from using this method of interstellar travel? Well, like most great ideas, the Bussard Ramjet comes with a few minor complications. Okay, maybe major complications. The first issue is the hydrogen density. The space is big and it's mostly empty. The interstellar medium has an average density of about 1 hydrogen atom per cubic centimeter. That's less dense than the best vacuum we can create on Earth. To collect enough hydrogen, the magnetic scoop would have to be massive. Secondly, at very high speeds, collecting hydrogen could create drag, meaning the spacecraft would slow itself down as it scoops up more particles. This could cancel out the thrust generated by fusion, making the whole thing inefficient. Fusion technology is another problem with the Bussard Ramjet. We don't yet have a reliable way to produce controlled nuclear fusion on Earth, let alone in space. And even if we did, compressing and igniting hydrogen at the rate needed for a Bussard Ramjet would be challenging, to say the least. Since Bussard first proposed the concept, scientists and engineers have come up with a few modifications to make this idea more practicable, but we have yet to come up with a workable plan. Ion thrusters. Picture this. You are on a sleek, futuristic spacecraft gliding effortlessly through space. No roaring engines, no fiery exhaust, just a faint blue glow as your ship accelerates to your destination, a star. But how can a space shuttle not make any sound? The answer? Ion thrusters. For those of you who haven't watched Star Wars, ion thrusters are like the tortoises of the space race. They may not be the fastest, but they are efficient and reliable, which is exactly what you will need when you decide to go on interstellar travel. This method uses electric fields to accelerate ions to mad speeds, and we are talking about 90,000 miles per hour mad. But how does an ion thruster work? The process begins with a gas, typically xenon. Why xenon? Well, it's heavy, stable, and frankly, it sounds cool. The xenon atoms are bombarded with electrons, turning them into positively charged ions. These ions are then accelerated by an electric field and expelled out of the engine, creating thrust. Now, let's address the elephant in the room. Ion thrusters are not going to win any drag races. Their thrust is so low that if you were to strap one onto your car, it wouldn't even budge. Seriously, the force they generate is about as strong as the weight of a piece of paper. But here's the catch. We are going to use them in space, so without any air resistance or friction, even a small force applied consistently over time can result in impressive speeds. Unlike the methods we have discussed earlier, ion thrusters aren't just theoretical. They've already made their mark in space exploration. One of their earliest usages came in NASA's Deep Space One, which zipped around the asteroid Braille and the comet Borrelly using an ion engine. Then there's the Dawn spacecraft, which explored the asteroid belt and visited the dwarf planet Ceres, making it the first spacecraft to orbit 2 extraterrestrial bodies. NASA used ion thrusters for these missions because of fuel efficiency. Traditional rockets drink fuel like a sports car on a road trip, but ion thrusters sip it like a hybrid vehicle. This makes them a perfect choice for long-duration missions, where every ounce of fuel counts. And now the million-dollar question: can ion thrusters take us to the stars and help us achieve interstellar travel? The short answer is not on their own. While they are great for cruising around the solar system, they don't have enough punch to overcome the immense distances involved in interstellar journeys. Remember, space isn't just big, it's mind-bogglingly big. Even at their top speed, an ion-powered spacecraft would take tens of thousands of years to reach the nearest star. But they could be combined with other propulsion methods like nuclear fusion or solar sails to handle course corrections or slow the spacecraft down upon arrival. Ion thrusters are already impressive, but scientists are trying to find ways to make them even better. For instance, newer designs are exploring the use of alternative gases like krypton, which are cheaper than xenon. Yes, krypton, just like the home planet of Superman. So, if your spacecraft ends up powered by krypton, just remember, you're technically traveling on superhero fuel. They may not be the flashiest propulsion method, but ion thrusters are undeniably cool in their own right. So the next time you watch a sci-fi movie and see a spaceship with a glowing blue engine, you'll know it's not just for show. That's an ion thruster, quietly doing its job, one ion at a time. And who knows, maybe we will be using these thrusters for actual interstellar travel. Daedalus Interstellar Spacecraft. Imagine you are in the 1970s. Bell-bottom jeans are in, disco is dominating, and a group of brilliant scientists decides to plan humanity's first interstellar spacecraft. This wasn't just daydreaming. It actually happened, and the project was known as Daedalus. Project Daedalus was a study conducted by the British Interplanetary Society between 1973 and 1978 to design a spacecraft to travel to a nearby star system. The goal was simple but audacious: design a probe capable of reaching Barnard's star, which isn't too far, just a little over 5.9 light-years away from us. Even at speeds that would make, another Star Wars reference alert, the Millennium Falcon blush, getting to Barnard's star would take decades. But the British Interplanetary Society team was determined to achieve this, because you're aiming for the stars, quite literally, why settle for anything less? The Daedalus spacecraft was planned as a two-stage nuclear fusion-powered machine. That's right, this thing wasn't going to run on rocket fuel, it was going to use the power of the stars themselves. How? The spacecraft would use pellets of a fusion fuel mix, primarily helium-3 and deuterium. These pellets would be fed into a reaction chamber at a rate of 250 per second, where they'd be ignited by electron beams, producing a series of controlled nuclear explosions. Think of it as a cosmic version of shaking up a soda can, except if the soda was radioactive and the can was the size of a bus. The energy from these explosions would be directed out the back of the spacecraft, propelling it forward at mind-boggling speeds. How fast? The goal was 12% of the speed of light, or about 36,000 kilometers per second. At that pace, Daedalus could reach Barnard's star in just over 50 years, which is a blink of an eye in cosmic terms, but about 2 generations in human terms. As for the size, Daedalus wasn't small. At over 190 meters or 623 feet long, it would have made even the Saturn V rocket look like a baby in front of it. The first stage alone would burn for 2 years, accelerating the spacecraft to nearly 7% of the speed of light before being jettisoned. Then the second stage would kick in, pushing it the rest of the way at 12% of the speed of light. Just like its design, the payload capacity of Daedalus was also impressive. It would carry a massive 450-ton of payload, including telescopes and other scientific equipment to study Barnard's star and its hypothetical planets. It even included an autonomous probe to descend to any planets it found, because why stop at go big when you can also go bold? So, or all its brilliance, why did Daedalus remain just a concept? For starters, building an interstellar spacecraft costs a lot, and by a lot, we mean more than most countries could afford. Secondly, making the spacecraft was one thing, fueling it was another. Helium-3, the magic ingredient for its fusion reactor, is incredibly rare on Earth. So rare that anyone familiar with its availability would laugh and say, "Good luck, buddy," if you ask them for it. And let's not forget the factor of human patience. A 50-year mission is a tough sell, especially when the people launching it wouldn't live to see the results. Even though it never got off the drawing board, Project Daedalus proved that interstellar travel wasn't just the stuff of science fiction. It was, and still is, a possibility. Daedalus also inspired later projects like Project Icarus, a modern update to the original design. But could we build Daedalus today if we wanted to? Theoretically, sure. Practically, not quite yet. While we have made some great advances in science and technology, there's still a long way to go before we can slap a fusion engine onto a spacecraft and call it a day. Plus, there's the small matter of figuring out who's going to pay the bill. Elon Musk, Jeff Bezos, a galactic bake sale. Daedalus was humanity's first serious attempt to design a ship for the stars. It wasn't perfect, but it was bold, ambitious, and just crazy enough to spark the imagination of countless scientists. So, the next time you look up at the night sky, remember, somewhere, someone is probably sketching out the next Daedalus. And who knows, maybe the first starship won't just be a concept, maybe it'll be called Daedalus 2.0, with a side of disco, for old time's sake. Solar sail. Ever thought about a spaceship moving through the galaxies powered by nothing but sunlight? No fuel tanks, no noisy rockets, just a giant shiny sail catching rays like an interstellar surfer. At its core, a solar sail is exactly what it sounds like, a sail that uses the sun to move. But instead of wind filling its sails, it uses light. Yes, light! Wait, the light has a push? It does. Photons, the particles of light, don't have mass, but they have momentum. When they bounce off a reflective surface, they transfer a tiny bit of energy. Multiply that by the trillions of photons hitting a giant sail, and you've got enough force to move a spacecraft. So, how does a solar sail work? It's made of an ultra-thin, highly reflective material, often something like mylar or captain, stretched out over a large frame. These materials are so light and shiny that they make even disco balls jealous. The sail is spread out in space and catches sunlight to generate thrust. Here's something interesting. The force from sunlight is small, extremely small. If you slapped a solar sail onto your car, it wouldn't even budge. But in the vacuum of space, where there's no air resistance or friction, even a tiny push can add up over time. The result? A spacecraft that just keeps accelerating. The best part of solar sail? Once you've deployed it, it's free energy forever. The sun keeps shining, and your ship keeps moving from one star to another. And without heavy fuel tanks, solar sail spacecraft can be incredibly light and efficient, giving you propulsion as long as there's sunlight, or might I say starlight. The good news is that solar sails aren't just theoretical. They've already been tested. The first famous example is Icarus. Launched by Japan in 2010, this was the first spacecraft to successfully use a solar sail for propulsion. Icarus deployed a sail about the size of a volleyball court and used sunlight to change its trajectory, proving the concept worked. LightSail 2 was another successful test case. Funded by the Planetary Society and launched in 2019, this spacecraft showed how solar sailing could raise a satellite's orbit using only the power of sunlight. But despite these successes, solar sails aren't perfect. For one, they are not exactly top of the line when it comes to speed. It's like pushing a shopping cart uphill with a straw. Another issue is the size of the sails needed for serious interstellar travel. We are talking sails several kilometers wide. Putting something that big in space without it turning into a giant failure is no small task. And then there's the problem of wear and tear. Space might look empty, but it's filled with tiny particles and radiation that could damage the ultra-thin sail material. Imagine trying to cross the Pacific Ocean with a sail made of tissue paper. Despite the challenges, solar sails hold incredible promise for future space exploration, especially interstellar travel. A large enough sail could reach speeds of 20% of the speed of light when pushed by a powerful enough light source, like a laser array. Projects like Breakthrough Starshot are already exploring this idea. And in case you were wondering if we could build a starship with solar sailors, the answer is absolutely yes. It might take some time, but imagine a fleet of tiny spacecraft, each equipped with a solar sail and powered by lasers on Earth or in orbit. These miniature starships could travel to nearby star systems, sending back data about alien planets or alien life. Sure, it sounds like something out of a sci-fi movie, but the technology is real and the potential is huge. Plus, how cool would it be to say that humanity's first interstellar spacecraft wasn't some noisy rocket, but a silent, graceful sail gliding through the stars? So, the next time you are taking a sunbath, remember that the same light warming your face could one day carry a spacecraft to the stars. Magnetic sail. Can you imagine a spaceship with an invisible bubble around it that grabs hold of charged particles and rides them across the universe? That's the magnetic sail, or mag sail, and it's one of the coolest and most sci-fi sounding methods of interstellar travel we've got. A magnetic sail, which was initially proposed by Andrews and Zubrin in 1988, is basically a force field. Yes, the kind you have seen in sci-fi movies, except this one is real. Here's how it works. First, you generate a strong magnetic field using superconducting loops or coils. This magnetic field interacts with charged particles, like the ones streaming out from the sun in the form of the solar wind. These particles push against the magnetic field, and voila! Your spacecraft gets a gentle but continuous shove in the right direction. It's like putting up a sail in a windstorm, except the wind is made of electrified plasma and your sail is invisible. Although the push from a magnetic sail isn't huge, it's enough for a resistance-free space. The solar wind typically travels at speeds of 400 to 800 km/s, or about 1 million miles per hour. By catching this stream of charged particles, a magnetic sail can slowly accelerate a spacecraft to high speeds. The longer you let it ride, the faster it goes. You might be thinking, this sounds a lot like a solar sail. What's the difference? Great question. While solar sails depend on photons, magnetic sails work with the charged particles in the solar wind. Here's a kicker. The force from the solar wind is actually stronger than the push from sunlight. Plus, unlike a solar sail, a mag sail doesn't need to be a giant reflective sheet. Magnetic sails can also do something else that solar sails cannot. They can slow down at your command. By flipping the orientation of the magnetic field, a mag sail can use the solar wind to slow down, which is super handy when you're trying to stop at your destination instead of zooming past it like a kid on a runaway sled. But of course, nothing is ever as easy as it sounds in space. Firstly, generating a strong magnetic field requires superconductors, which need to stay extremely cold to work. Space is pretty chilly, but keeping superconductors stable is still a technical challenge. Another issue is the solar wind. It isn't exactly predictable. A sudden solar storm could push your mag sail off course or even damage your spacecraft. And lastly, it's the weak magnetic force of the solar wind. While the solar wind is stronger than sunlight, it's still not going to break any speed records. We know that no magnetic sail has flown yet, but the concept has been studied extensively. One ambitious idea involves combining magnetic sails with beam-powered propulsion, which we are going to talk about later in the video to give the sail an extra push. Magnetic sails are the quiet geniuses of space propulsion, and we may be seeing the idea come to life very soon to take us to the stars. Wormholes. If you're on a road trip and spot a tunnel that cuts straight through the mountain, taking you from point A to point B in record time, you would take it, right? Now imagine that tunnel works not just for highways, but for the entire fabric of space and time. We are talking about wormholes, which are theoretical shortcuts through the universe that could make interstellar travel as simple as stepping through a door. In scientific terms, a wormhole, also known as an Einstein-Rosen bridge, is a hypothetical tunnel in space-time. Picture the universe as a giant piece of paper. Now, fold that paper in half so two distant points touch. A wormhole is like punching a hole through those points and creating a shortcut between them. It's all thanks to Einstein's general theory of relativity, which tells us that massive objects like stars and black holes can warp space-time. Wormholes take this concept to the extreme, bending space into a cosmic pretzel that lets you move from one end to another quicker than you can imagine. But if we wanted to travel interstellar using a wormhole, how exactly would that work? First of all, we'll need to locate or create the wormhole. Easy, right? Just find a naturally occurring wormhole somewhere in the galaxy, or, build one using hypothetical exotic matter. Once step one is done, it's time to set up the entrance. Think of the wormhole as a two-way portal. One end could be near Earth, and the other might pop out in a completely different galaxy. After the second, all that's left for us will be stepping through it to a completely different and unknown world. But travel through the wormhole would feel instantaneous. No warp drives, no cryogenic sleep, just a quick hop through the cosmic tunnel. The best part of wormholes is that you'd be skipping the boring middle part of space travel. No more "are we there yet?" Just, "whoa, we're already here?" But only if using such a quick method of interstellar travel was so easy. Wormholes, if they exist, are inherently unstable. The second anything tries to pass through, like a spaceship or even a stray particle, they'd collapse faster than a poorly built sandcastle. Also, to keep a wormhole open, you'd need something called exotic matter, which isn't your average table salt or bottled water. This is a hypothetical type of material with negative energy density, and we're not even sure it exists. If it does, we'd need a lot of it. But even if we are able to find or create a stable wormhole, the tidal forces near its edges could be so strong that they'd shred you into atomic confetti before you even get to enjoy the ride. And here's where things get really weird. Wormholes don't just connect 2 points in space. They might also link 2 different points in time. So you could theoretically use a wormhole to go back in time and accidentally prevent yourself from inventing the wormhole in the first place. Oops, the next question is, do wormholes exist naturally in the universe? We don't know the answer to that because even if they are out there, we haven't found one yet. That's not surprising, considering they'd probably be tiny, like subatomic tiny. The good news? Some physicists believe it might be possible to artificially expand a wormhole using advanced technology, so we could one day make them big enough for spaceships to pass through. And if we do find a naturally occurring wormhole, let's just hope it doesn't dump us into the middle of a black hole or a universe made entirely of shrimp, unless you are into that sort of thing. While we have seen wormholes in movies like Interstellar, they are the ultimate what-if in actual interstellar travel. What if we could create stable ones? What if we could produce exotic matter? What if we could pop over to the Andromeda Galaxy for lunch and be back in time for dinner? So, while we're busy figuring out how to make magnetic sails or fusion engines work, let's not forget that we have shortcuts through space and time too. Chemical rockets. Chemical rockets are the classic hero of space exploration. It's the technology that got us to the moon, launched satellites into orbit, and sent probes on epic journeys across the solar system. But when it comes to interstellar travel, chemical rockets are like trying to cross the Atlantic in a rowboat. Technically possible, but you'll probably need several lifetimes and an unhealthy obsession with canned food to make it work. Chemical rockets are basically flying fuel tanks. They rely on a chemical reaction between fuel and an oxidizer to produce high-pressure gases. These gases are then expelled out of a nozzle at blistering speeds, creating thrust. It's basic physics. Every action has an equal and opposite reaction. So as the rocket pushes the exhaust backward, the exhaust pushes the rocket forward. Think of it as blowing up a balloon and letting it go. But instead of a balloon, it's a metal cylinder packed with explosives, and instead of floating across your living room, it's tearing through the atmosphere at Mach 33. Now, here's the thing. Chemical rockets are awesome for local travel. They have been our go-to method for getting humans and robots into space for quite a few decades now. But interstellar distances? That's a whole different beast. For context, the closest star system, Alpha Centauri, is about 40,000 billion kilometers away. And even if you hopped on the New Horizon, one of the fastest chemical rockets we've ever built, with a speed of 36,000 miles per hour, it would take you nearly 100,000 years to get there. That's longer than human civilization has existed. But time isn't the only issue here. Fuel is an even bigger hurdle. Chemical rockets need a ridiculous amount of it. Let's say you wanted to send a spacecraft the size of a school bus to Alpha Centauri. You'd need so much fuel that your rocket would be larger than some small countries. Here's a fun fact. During launch, most of a rocket's weight is just fuel. The Saturn V, the rocket that took humans to the moon, weighed about 50,000 kilojoules fully fueled, but only about 10% of that made it back to the Earth. The rest? It was mostly fuel that got burned in the process of taking humanity to the moon. Now, imagine a rocket for interstellar travel. You'd run out of materials, money, and patience before you even left Earth. Chemical rockets also suffer from low efficiency compared to other propulsion systems. Their exhaust velocity, the speed at which gases leave the rocket, is limited by the energy released in the chemical reaction. This means you need an absurd amount of propellant to achieve high speeds, which is a bit like trying to fill a swimming pool with a garden hose. But despite all these issues, can chemical rockets be modified and improved for interstellar travel? Theoretically, yes, but only to a point. Engineers have experimented with advanced designs like staged combustion cycles and better propellants, but these tweaks are like putting a turbocharger on a lawnmower. It helps, but you're still not winning any races. Some latest ideas include using multi-stage rockets or pairing chemical rockets with other propulsion systems, like ion thrusters or nuclear engines. But even then, they'd only cut a few thousand years from your journey. Let's not be too hard on chemical rockets, though. They have achieved incredible feats in the past. Without them, we wouldn't have walked on the moon, explored Mars, or sent probes to the outer reaches of the solar system. And while they may not be suitable for interstellar travel on their own, they could still play a role. For example, they could be used to launch components of more advanced spacecraft into orbit, where those spacecraft could assemble and prepare for interstellar travel. Think of them as the cosmic Uber drivers, getting you to the airport so you can catch your flight on a much faster interstellar craft. Laser beam-powered propulsion. Picture this. You are sitting in your backyard, aiming a laser pointer at your cat, watching it go bonkers trying to catch that little red dot. Now what if we scale up that laser pointer to something powerful enough to push a spacecraft to another star system? This isn't science fiction. Well, mostly not. Rather, it's one of the most promising ideas for interstellar travel, where lasers would be used to propel lightweight spacecraft to mind-boggling speeds. Laser beam-powered propulsion is all about using high-energy lasers on Earth, or in orbit, to push a spacecraft using light. The spacecraft would carry no fuel because fuel is heavy, expensive, and kind of a buzzkill when you are trying to travel light years. Instead, the laser's photons would exert pressure on a sail attached to the spacecraft, accelerating it to incredible speeds. If this sounds like a solar sail, you're not wrong. It's a similar principle, but with one key upgrade. Instead of relying on the sun's light, you are using a high-powered laser. It's like trading your bicycle for a rocket-powered skateboard. Alright, we have decided to use laser beam power propulsion for interstellar travel. How will it work? First, we will need to build an enormous, high-powered laser. Once done, we will need to aim it at a lightweight spacecraft that has a reflective sail on its back. The last step is fun. Fire the laser and watch as the photons bounce off the sail, transferring momentum to the spacecraft and sending it flying through space. The idea is that you can keep the laser beam focused on the spacecraft over long distances, continuously accelerating it until it reaches a significant fraction of the speed of light. So, where does it rank among the methods of interstellar travel in terms of speed and efficiency? Well, using current concepts, a laser-propelled spacecraft could potentially reach 20% of the speed of light. That's fast enough to make the journey to Alpha Centauri in about 20 years. Compare that to the thousands of years it would take with chemical rockets now. It's like upgrading from a tricycle to a Formula One car. If we can get to our nearest star in 20 years, then why haven't we built a laser beam-powered propulsion system yet? For starters, building a laser powerful enough to propel a spacecraft to relativistic speeds would require a lot of energy. We're talking about energy levels that make the Hoover Dam look like an AA battery. And then we have the aiming problem. Keeping a laser beam precisely focused on a tiny spacecraft millions of miles away is like trying to shine a flashlight on a mosquito that's buzzing around on the other side of the planet. Let's not forget the heat problem either. All that laser energy hitting the spacecraft's sail could easily turn it into a very shiny puddle. Scientists are working on materials that can handle the intense heat without melting like a popsicle on a summer day. And once the spacecraft reaches its destination, there's the issue of slowing down. Spoiler, it can't. These probes would zoom past their target at full speed, snapping pictures and collecting data on the fly. It's a one-way, high-speed sightseeing tour. So, while we may still be a long way from building the Death Star, laser propulsion could be our first step toward becoming an interstellar species. And if that doesn't make you want to grab a laser pointer and start practicing, I don't know what will. Antimatter propulsion. Let's face it, when it comes to interstellar travel, most propulsion ideas sound like they were ripped straight from a sci-fi blockbuster. But then, there's antimatter propulsion, which feels so over-the-top futuristic that even the writers of Star Trek probably said, yeah, let's save that one for later. Antimatter is exactly what it sounds like, the evil twin of ordinary matter. For every particle of matter, like a proton or an electron, there's a corresponding antiparticle, like an antiproton or a positron. These antimatter particles have the same mass but opposite charge. Now, here's where things get spicy. When matter and antimatter meet, they destroy each other in a burst of pure energy. No leftovers, no crumbs, just raw, unfiltered energy. Following Einstein's famous equation, E equals to mc squared. This releases millions of times more energy per unit of mass than chemical reactions, making antimatter the ultimate rocket fuel. In theory, just a few milligrams of antimatter could produce the same energy as hundreds of tons of conventional rocket fuel. Talk about packing light. So, how would an antimatter propulsion work for interstellar travel? Well, the behind antimatter propulsion is surprisingly straightforward. First, you will need to produce antimatter, which is easier to say, extremely hard to do. But let's say you somehow successfully completed stage 1, you will now need to store the antimatter safely. Again, easier said than done because remember, this stuff annihilates on contact with matter. If you come out of the first 2 stages alive, we will need to mix it with ordinary matter in a controlled reaction to produce a massive burst of energy, and use that energy to propel your spacecraft at speeds that make chemical rockets look like toy cars. The most common concept involves combining antiprotons with regular protons in a reactor. The resulting annihilation generates high-energy particles, which are then directed out of a nozzle to produce thrust. As for the prospects of this method of interstellar travel, antimatter rocks, both literally and figuratively. Antimatter propulsion could theoretically push a spacecraft to 10% to 50% the speed of light. At those speeds, you could reach Alpha Centauri in as little as 8 years. Compare that to the thousands of years it would take with current technology, and suddenly, interstellar travel starts seeming fun. Another perk? Unlike chemical rockets, which require gigantic fuel tanks, antimatter propulsion is incredibly efficient. A tiny container of antimatter the size of a sugar cube could, in theory, take you to the stars, and it wouldn't even weigh you down. Rather, it'd probably be the lightest part of your luggage. Current estimates suggest that producing just 1 gram of antimatter would cost about $62.5 trillion. To put that in perspective, the current GDP of the United States is $29 trillion. And for the price of a gram of antimatter, you could buy enough avocado toast to last several millennia, and that's assuming you can even produce it in the first place. Right now, all the antimatter humans have ever made wouldn't even fill a teaspoon. The production process is inefficient, requiring huge particle accelerators and mad amounts of energy to create even a few particles. Then there's the storage issue. Since antimatter annihilates on contact with matter, you can't just toss it in a jar and call it a day. But if we could overcome these challenges, and that's a big if, antimatter propulsion could revolutionize space exploration. Trips to Mars could take weeks instead of months, and journeys to the outer planets could be measured in months instead of years. Plus, antimatter propulsion is so efficient that it could allow for much larger payloads. Want to bring your favorite couch to Alpha Centauri? With antimatter, you just might be able to. However, for now, antimatter propulsion remains only in the category of cool ideas that are wildly impractical. But hey, so was the airplane once upon a time. So it's just a matter of figuring out the science and, you know, the trillion-dollar price tag. But after we figure everything out, just make sure you don't accidentally annihilate the home planet on your way out. Cryogenic sleep. What if you could press a button, go to a long, deep sleep, and wake up centuries later without aging even a day? Cryogenic sleep is a concept straight out of sci-fi movies where humans are put into a state of deep hibernation for extended periods by lowering their body temperature to near freezing. It's like a long winter nap, minus the dreams, because your brain isn't exactly firing on all cylinders. The idea is simple. Freeze yourself safely before the trip and wake up when you've reached your destination. Think of it as skipping all the boring parts of the journey. No boredom, no claustrophobia, and best of all, no space food. But this method of interstellar travel isn't only about science fiction. There's some real science involved behind it too. Here's how it could work. The first goal would be to slow down your body's metabolic processes so you require less oxygen, food, and water. But is that possible? I mean, animals like bears and squirrels do this naturally during hibernation, so why not humans? The next step involves cooling the body to extremely low temperatures. But that comes with issues like ice crystals shredding your cells. That's gonna hurt, but the good news is scientists are exploring hypothermia-induced hibernation, where the body is cooled just enough to slow things down without turning you into a popsicle. You would also need a cryopod that would monitor your vitals, give you essential nutrients, and keep your systems in tip-top shape while you snooze. So, basically, you will have your personal healthcare team, except that they won't talk back. While the method sounds cool, it isn't without its fair share of challenges. First of all, cryogenic sleep could lead to muscle atrophy, bone loss, and other complications from long-term inactivity. Plus, there's the small matter of not accidentally freezing someone to death. Secondly, what happens if the pod malfunctions mid-journey? It's not like you can call customer service from deep space. And there's the psychological impact. I mean, imagine waking up to realize everyone you know and love is long gone. That's a heavy burden, even if you're sipping cocktails on an alien beach. Cryogenic sleep is the ultimate wake me when we get there technology. It's not perfect, but it's a catchy solution for the mind-boggling distances between stars. So, if you're ever offered the chance to nap your way to Alpha Centauri, just make sure they have worked out the whole not dying in your sleep thing first. Generation ship. Imagine this. You board a spaceship bound for a distant star. You pack your stuff, wave goodbye to Earth, and never actually arrive. Not you, your kids, or even your grandkids. In fact, by the time the ship reaches its destination, your name is just a footnote in the onboard history books. Welcome to the wild and wildly slow world of generation ships, where patience isn't just a virtue, it's the whole mission. Generation ships are the tortoises of interstellar travel, slow, steady, and deeply committed to the long game. They may not have warp drives or antimatter engines, but they offer something those flashy concepts don't: actual feasibility. Well, sort of. As the name suggests, a generation ship is a spacecraft designed to support multiple generations of humans on a journey to another star system. Think of it as a self-sustaining city in space, complete with farms, schools, and probably a lot of arguments over whose turn it is to do the laundry. Since faster-than-light travel still remains in the maybe someday category, generation ships take a more realistic approach. They acknowledge that journeys to even the nearest stars could take thousands of years with current or near-future technology. So, instead of trying to shorten the trip, they make the ship itself a permanent home for its passengers and their descendants. The basic idea of a generation ship is simple. You build a massive spaceship, load it with everything humanity needs to survive indefinitely, and point it toward a star. Easy, right? Not so much. Firstly, a generation ship has to be entirely self-sufficient. That means growing its own food, recycling its air and water, and possibly even mining asteroids for resources along the way. And with space and resources limited, the ship's population has to stay within strict limits. This could mean anything from careful birth control to some kind of dystopian lottery system. Let's hope it's the former. Let's not forget the long-term survival of the ship, because over centuries or millennia, the ship's systems will degrade, and its people might face social, political, or even philosophical crises. How do you convince Generation 128 that the distant star they've never seen is worth the effort? Also, spending your entire life inside a metal box isn't exactly a dream vacation. Even with virtual reality or carefully designed habitats, it could become a serious problem. Think of it as a lockdown, but for eternity. We are also aware that even the best engineered systems fail eventually, so keeping a spacecraft operational for thousands of years would require either near miraculous maintenance or technology we haven't yet invented. And over centuries, the ship's society might evolve in ways the original planners never anticipated. What happens if they decide they don't care about reaching the destination anymore? And lastly, is it fair to consign future generations to a mission they didn't choose? It's a question philosophers would argue about endlessly, only if they weren't too busy fixing the oxygen scrubbers. So, if generation ships are slow, risky, and full of ethical dilemmas, why even consider them? Because they might be the best and the only option for humanity's long-term survival. While faster propulsion technologies like antimatter engines or warp drives remain theoretical, generation ships could be built with technology already available. Therefore, in a few years, you might find yourself aboard a generation ship. And if you do, remember, it might not be fast, but it beats spending eternity stuck in Earth's orbit arguing over which streaming service to watch.